Let's continue with our fluid mechanics series. Today we are dealing with a special property called viscosity, and I think it deserves its own video. So let's look at what viscosity is, what it does for fluids, and how it is affected by other properties like temperature. So I'd like us to watch a short animation to see how fluids are affected by shear forces. So here we have a substance that is arranged in layers, but there is no force of attraction between the layers. Any applied shear force will just move that particular layer without affecting the rest of the substance. Fluids, however, have some force of attraction between their layers. Therefore, when one layer moves, it pulls the rest of the fluid along with it. And we are going to base on this idea to define viscosity and how it works in different fluids. So simply put, viscosity is just the internal resistance within a fluid or any substance. And this is as a result of layers of that fluid sliding over each other. And we know whenever things slide over each other, there should be some form of friction. So that friction is what causes the layers to resist the flow. Let's use a very thin layer of fluid or thickness of fluid to generate the mathematical formula for viscosity. Let's represent the thickness of the fluid by dy. And we saw that an applied shear force will cause the layers to shift in the direction of the force. So let's represent that movement or that distance by dx. Also, once there is movement, then that movement will be at a certain velocity. And from what we saw, the topmost layer will move with the fastest speed because it is the one that moves in the longest distance within the same time frame. So each layer will move at a different velocity. The difference in the movement of each layer will cause a deformation. So let's represent that angle by d theta. Then from our trig ratios, we know that tan of any angle is just equal to the opposite over the adjacent. So let's come down here and then look for tan of d theta, where we are going to have tan of d theta equals dx over dy. However, we are dealing with a very small layer of fluid, so we are going to see a very small deformation, which means the angle will be very small. Now the tan of small angles, especially in radians, is almost the same angle. So let's say the tan of 0.0005 in radians is equal to 0.0005. So that we can write tan of d theta is proportional to d theta. When we do this, our formula now becomes d theta equals dx over dy. We also know from physics that the change in speed in any substance is equal to the change in distance over the change in time. So by doing the substitution, we have the theta equals the u dt over the y. Now let us rearrange so that we have the theta over the t equals the u over the y, and let's explain what that means. So from what we have, we can say this. 1. The deformation is represented by the angle, so the change in deformation with time is proportional to the change in speed, and that change in speed is along the y-axis. Or indirectly, different layers move with different speeds when we move along the y-axis. The applied shear stress is proportional to the change in deformation with time, so let's just call the theta over the t shear stress, and that is represented by the Greek letter tau. Then we can also say that this change in deformation is not the same in all fluids, because when we compare water and honey, the flow is not the same. Then we need to introduce a constant to account for the behavior of different fluids. So that constant is supposed to represent how different fluids behave under a shearing force or a shearing stress. Once you've been able to establish that formula, let's move on to a condition called the no-slip condition, and this occurs as a result of viscosity. Let's visualize a fluid that is flowing through a pipe. So we can use this idea that most fluids tend to stick to the surface of solids, especially when they are flowing through them or they are just static in the solid or in their container. Then this force of attraction with the solid surface is sometimes stronger than the force of attraction within the fluid particles themselves, which means that the layer just close to the solid surface or the boundary is attached more closely to that solid than to the adjacent layer of the fluid itself. Another fact we must state is that liquids cannot flow through impermeable solids. Therefore, at the boundary, there will be no movement, or the liquid would have to stop because it cannot flow through the solid surface. As a result of this, fluid motion at the boundary is zero. That is where the fluid and the solid boundary meet. We say there is no movement, and the velocity of the fluid is the same velocity of that boundary or of that solid. Then once we have stated that, we can also say that as we leave the boundary where there is zero movement, the speed of the fluid particles or the layers begin to increase, so that the highest velocity will be at the center. So at the boundary layer, there is no movement. This is called the no-slip condition. An example we can give for the no-slip condition is this. Buy a brand new pipe and let clean water flow through it. After some time, the inside of the pipe becomes dirty because there is no movement at the solid-liquid boundary, and particles can stay there, which causes the pipe to be dirty. So what we have seen so far is known as dynamic viscosity. There is another one called kinematic viscosity. So let's look at the difference between dynamic viscosity and kinematic viscosity. So dynamic viscosity is represented by the Greek letter mu, and kinematic viscosity is represented by the Greek letter nu. So let's look at the difference. Dynamic viscosity measures the internal resistance of a fluid as it is affected by shear forces or shear stress, or when it is flowing. Kinematic viscosity measures the resistance to flow under gravity. Also, dynamic viscosity depends only on the fluid's internal resistance, but kinematic viscosity depends on both the dynamic viscosity and the density of the fluid. So we've already seen the formula for the dynamic viscosity. Now the formula of kinematic viscosity is the dynamic viscosity divided by the density. And we can also use their units to differentiate them. The unit of measurement for dynamic viscosity is the Pascal second or the Newton second per meter squared, and that of kinematic viscosity is the meter squared per second. and we can always use the formulas to generate these units. Now let's look at how temperature affects viscosity of different fluids. Now at low temperatures, the viscosity of liquids is high because there is no energy to break the bonds between the liquid molecules or the liquid layers. So for instance, oil in a fridge behaves as if it is becoming a solid that is high viscosity. The moment we put fire under this cold oil, we realize that it begins to flow easily. What this means is that the energy from the heat has broken down some of the attractions between the layers such that they can easily slide over each other. So we can draw a graph that shows the change in viscosity as temperature increases. Then realize that as the temperature goes up, the viscosity goes down. However, for gases, the effect is in the reverse. So let's see another way of looking at viscosity. You know, when the fluid is very thick, then it becomes very easy for substances to flow through, and a thick fluid has high viscosity. So another way of looking at viscosity is how easy an object can flow through the fluid. We know gas particles are almost on the move, so at low temperatures, the motion of the particles in a gas is relatively slow because they possess low kinetic energy. That is, the energy they require to move with speed is very low. That is when the gas is at a low temperature. However, at high temperatures, the gas particles receive enough energy to move with speed, and if they are moving at very high speeds, then it becomes very difficult for an object to flow through. So we say at high temperatures, the viscosity of gases is also high, and at low temperatures, the viscosity reduces. Unlike a liquid, where at high temperatures, the viscosity is low, and at low temperatures, the viscosity is high. So once we know the viscosity changes with temperature, let us look at how to determine the viscosity of fluids at different temperatures. So we are going to look at that of liquids and that of gases. So because liquids and gases don't behave in the same way when it comes to how temperature affects their viscosity, we have to look at the formulas that are used to determine unknown viscosities at certain temperatures. For gases, we use the Sutherland's equation to determine the viscosity at an unknown temperature. So the Sutherland's equation basically says that if you know the viscosity of a gas at a particular temperature, then we can use this formula to determine the viscosity of that gas at another temperature, whether the temperature is lower or higher. So the S in the Sutherland's equation is just the Sutherland's constant, and every gas has its own Sutherland's constant. So when we start solving questions with these formulas, we'll see the Sutherland's constants of certain gases and how to use them in this formula. For liquids, we use what we call the Andrade's equation, which has two constants that are unknown. So before we can use this equation, we need to determine those two constants, and we can only do that by solving simultaneously. So like I said, we'll look at how to use these equations in the next video, where we'll solve questions with all the formulas that we have learned so far.